Welcome to lecture 3 of Dynamical Systems. During the last lecture, we derived the result that dynamical systems are unique and their solution exists provided given a certain set of initial conditions. And we further showed that in one dimension, the fact that you're moving along a line results in the fact, or you're restricted to the topology of the line, results in the fact that the solutions have certain predictable characteristics, namely they either monotonically increase or decrease to a fixed point, or they monotonically approach infinity. Now you might think that this is quite a restrictive condition on the types of solutions you have, and it is in fact. The dynamics in 1D are limited. The only way we get some interesting physics or models out of it is to study what we call bifurcations. Now bifurcations is how the fixed points change with a parameter in the dynamical system. And we'll be looking today at various kinds of bifurcations. It is actually possible to classify them in one dimension and subsequently in higher dimensions as well. And the advantage is in higher dimensions, all the lower dimensional ones are necessarily included. So let us now begin our study of bifurcations. For those following the textbook, we'll be dealing with bifurcations occurs in chapter 3 of Strogatz, whereas the one-dimensional dynamics I've just discussed occurred in chapter 2. Right, so let us define a bifurcation before we start studying them in detail. So firstly, a bifurcation is a qualitative change in dynamics and flow field as a parameter is varied. And we'll see several examples of this during this lecture. So in one dimension, and bifurcations occur in any dimension, but in one dimension, which is going to be the subject of this talk, we can describe it as follows. Suppose in one dimension we have x dot equals to f of x. Okay. The qualitative structure of the vector field can be changed by the following ways. Firstly, if for a different f of x you can either create or destroy fixed points as you change f of x, you can change the stability of your fixed points, and that's it. That's the only two possibilities you have. And remember that the solution always runs to either fixed points or infinity, so then you've basically described all the qualitative change of structures that you can have in one dimension, and you'll see this illustrated soon. So bifurcations, just to give you a more global picture of why we're interested in this, in science bifurcations occurs in many places. To name a few examples, one bifurcation is when the type of flow in water changes. You can go from laminar flow, which is like the smooth, slowly flowing river, to turbulent flow, which you see at the exit of a jet, where you have these turning vortexes. For example, a very good example in the Free State of turbulent flow is these massive cumulus clouds that we have just before a thunderstorm. There you can actually see the turbulent flow. You have all these round little eddies going up, whereas laminar flow, the lines are pretty much straight. Okay, and typically what you have is you have a knob that you can turn that gives you the transition. For example, there's a parameter in your differential equation. So for example, when you go to laminar to turbulent flow, the thing is the Reynolds number, which is basically a combination of viscosity and speed. So for example, if water flows slowly, it's going to be laminar, smooth flowing. As you increase the velocity, it's going to flow faster. But if you're flowing in syrup, you have to increase the velocity a lot more, because the viscosity of the syrup stops it from going turbulent, because it actually sticks and stops these eddies from forming. Whereas if you're flowing in a gas, because the viscosity is a lot less than water, you don't have to flow quite as fast to get turbulent flow in a gas. Another example of a bifurcation is a laser. In other words, a laser is formed by a bunch of atoms that emit light, and usually the light is not coherent, so it acts exactly as a lamp. But then something happens once you have enough atoms firing at the same frequency that they synchronize the emission, and you start the lasing state. Okay, and they call the parameter that changes the switch from a lamp just being an ordinary lamp that shines a light that's not in phase, that when it switches to actually being a laser is called the pump strength of the lasing molecules. Another example of a bifurcation is, suppose you're supporting a mass with a beam. So if the weight is small enough, the beam's going to be straight. But as you increase the weight more and more that you're stuck on top of the beam, eventually the beam's going to bend as you increase the load, and it's going to go one or two directions, and we'll see what type of bifurcation actually gives this. Another example of a bifurcation that is essential for life is you can view the functioning of the human heart as a solution to a dynamical system. And it's got one state in which it pumps with a clear beat that you see on all the electrocardiograms that people take whenever they want to explore your heart rate. But then there's another thing that can happen. If you change something in the heart or part of the heart muscle dies, you're no longer going to be in this healthy rhythm of a normal heart, but you're going to have a bifurcation to something they call ventricular fibrillation, which is basically where the heart goes like jelly. It can no longer pump the blood around the body, and that's basically what happens just before a heart attack. So here is a very interesting parameter, or important parameter, that people have tried to change. And in fact, Strogatz and one of his colleagues actually worked on this problem, on how you describe the heart to try and identify means in which you stop this type of ventricular fibrillation from occurring, especially if some of the heart muscle has died. Okay, so another fact, bifurcations are used to model transitions or instabilities. And so I just want to give you an example of a bifurcation in high dimensions that I'm very, very fond of. Okay, it's a simple example. It's called Rayleigh-Bénard convection. And so how this bifurcation is observed is, it's basically you have two see-through pieces, two plates of, basically they could be glass or they could be sapphire crystal. And you put the one at the bottom, you put the other one up top, and you have a very thin area in between that you fill, in this case, in many of the experimental cases, basically with carbon dioxide. And so what you do is you warm the bottom plate and you cool the top plate, and you see what happens. So in the lowest, if the difference is not very big, nothing happens. The gas just sits there. If once you warm it to a certain temperature difference, you start making these convection rolls. The warm air rises and then hits the top one, cools down, and then sinks down in these distinct rolls. And what people do is they shine light from below through these separate plates, and they can actually see the convection rolls because the different densities of the carbon dioxide gas bend the light. So if you take a picture of the situation, you're going to get something like this. So this is a real experiment. And this is at a certain temperature where the convection rolls are just straight lines. And now the fascinating thing, what happens if you increase the temperature? So here, the order parameter, or the parameter that says how the partial differential equation is changing, is just the temperature. If you increase the temperature, this pattern breaks up into a different type of pattern, and these things actually move. Okay, so this is just pictures of gas between these plates, but the temperature between the plates has a very important impact on what you actually see. And this is a typical, and people study this in great detail and work out the diagrams for which you get different kinds of patterns. Okay, so this is a little bit beyond the scope of the lecture, but I just wanted to show you a very beautiful problem, or that illustrates what a bifurcation is in a very detailed manner. So we're now going to start looking at bifurcations in 1D, where that's basically where all the modeling or models that you can get, and we're going to try and classify all of them, and it turns out that this is possible. But before I do that, I simply want to give you an example. Okay, so the first type of bifurcation we're going to study is called the saddle node bifurcation. And just to give you an idea of what's coming, it's a basic mechanism for creating and destroying fixed points. Now, people have studied bifurcations and they've, as I mentioned earlier, they've classified them, and we're basically going to look at all those that occur in one dimension. Okay, so there's a standard example, and that standard example is basically this problem. It's x dot equals to r, where r is a constant we're going to vary, plus x squared. And we call this form, when it's written like this, the normal form, and I'll show you subsequently why we call it that. Okay, and we're going to call r the parameter we're changing and that we study, as we're going to call it the control parameter. So the first thing we do when we get an equation like this, we simply explore it in the graphical way that we discussed in our second lecture. So let's do it for different possibilities of r. If we have r greater than 0, then we plot the graph. This thing is just x squared, so it's a parabola, it's in front, so it's an up-facing parabola, and r is the value of x dot when x is equals to 0. So here's the turning point. So we follow the same process as what we've done. We plot the graph, the rule that connects the velocity to the position, on the x dot x plane, which is basically our phase plane. We immediately then put in the arrows, so at every single point the graph is positive, so the arrows always go, or the flow direction along the x-axis is always to the right. There are no points at which the graph crosses the x-axis, so we know that the flow is basically going to go to positive infinity. Okay, so there are no fixed points here. Let's see now what happens as we decrease r. In other words, as we decrease r, this the x dot intercept is going to go closer to the x dot equals to 0, and so we have this intermediate case. If r is equals to 0, this parabola moves down, and it actually touches the x dot equals to 0 axis over here. And so what happens now, if we put in our arrows, if x is less than 0, the thing is increasing. If x is equals to 0, we have a fixed point. And if x is greater than 0, then it's also increasing. So we call this fixed point, where you sort of come in, get stuck at the fixed point, but push it a little bit beyond the fixed point, it's actually unstable and goes to infinity. We call this fixed point half stable. And now what happens if you decrease r even further? In other words, this graph moves down, or the x dot intercept becomes negative, and we now put in the arrows. We're going to have an positive arrow over here where the graph is positive, so here it moves to the right. Over here where the graph is negative, it moves to the left. Here it moves to the right. So if you start here, you go to infinity. If you start at any point from this fixed point to minus infinity, you're going to end up here at your stable fixed point. So we can immediately put in color in the circle over here for the stable and for the unstable fixed point that occurs here. Okay, so that's the geometric investigation. Now let's go further as well as what we did in the last lecture and actually do the analytic investigation. So just a few comments before I do that is just observe over here as r increases from negative infinity, the stable and the unstable fixed points, so these two sort of approach each other until eventually they reach each other. They then collide and disappear. Okay, so it gives you an idea of how the fixed points change as you change the parameter. And remember, all a bifurcation is studying how the nature of the solution changes as the parameter changes. And we also say now that the bifurcation occurs when the nature of the solution changes. In other words, when RC is equals to 0, and then we also say the point at which bifurcation occurs is when x star is equals to 0. So this is the bifurcation point over there. So let's just do the analysis we did previously. If we want to do it or give it a more analytic approach, we say firstly you have to take your differential equation, you find the fixed points, and the fixed points solve x dot is equals to 0. So we basically have x star squared plus r is equals to 0. And we're going to have to want to work out the stability analytically as well, just for completeness sake. So we work out f derivative at x star, and that's simply 2x star. And we know, therefore, that the fixed points occurs when x star equals minus the square root of minus r, and x star equals the square root of minus r. And if x star is equals to minus the square root of minus r, and we substitute this into this equation over here, we find that the fixed point is stable because the derivative is negative. In other words, we're down here at this example. Here the slope is negative, the fixed point is stable, which is something we've already got from the graphics. The other fixed point is x star equals the square root of minus r. Remember, r is negative in this case, and it's this fixed point. And we know that the derivative there is positive, which you can see from the graph or from our derivation over there, and therefore it's unstable. Okay, and this is true when r is less than or equals to 0. So just one comment, you're going to get a lot of cases where you solve polynomials in this case, and it is very, very important to always write down the conditions for the root to exist, right? In other words, whenever you write something like this down, you've got to always add the fact that r must be less than or equals to 0, because we're only dealing with real fixed points at the moment. Okay, and then the second thing is there are no fixed points for r greater than 0. Okay, so now we're going to introduce a third kind of diagram into this course. So remember, we had this diagram that gives you the phase space, which is x dot versus x. Then we had the physical trajectories, which was the graph of x versus t. And now we're going to introduce another plot, which we call a bifurcation diagram. This plot is only applicable when you're studying the bifurcations of a differential equation with a parameter r in it. And so what we do with a bifurcation diagram, we simply plot x, which is the fixed point, versus r, which is your control parameter. And so what we're doing here is we're basically going to plot these two branches over here. So here is our fixed points, x star equals to minus the square root of minus r. So if r is negative, we're over here, and what we're going to plot here is this basically fixed point as a function of the parameter. And what we're also going to do is we're going to indicate whether the fixed point is stable or not. And what we always do is we indicate stability with a solid line and an unstable fixed point with a dotted line. So we have our stable fixed point over here, and then we have our unstable fixed point over here. So this is the plot of x star equals to minus r, the square root thereof. So that's what we have over here. Okay, so this is what we call a bifurcation diagram. What I also do just to check, and this point over here, where the nature of the number of fixed points changes, is known as the bifurcation point. So what I also do whenever I plot a bifurcation diagram for each region, in other words, above any of these lines, I always put in the arrows. Okay, so suppose you have x greater than this graph, the flow will be upwards. You can simply pick a value from for x and r and pop it in here, and you see whether x dot increases or decreases, and the value is, in this case, it's increasing, decreasing over there, and increasing over there. In fact, you can notice that these purple arrows are exactly these purple arrows over here that have just been flipped on the side. And in fact, this line over here is just a stable fixed point by construction, and that is the unstable one. Okay, so then what we can also do is over here, we can once again put in the arrows for the r equals to 0 case, because r is equals to 0 over here on this axis. And then what we have is we're simply putting in these arrows where they approach the the origin, or x dot is equals to 0 from below, or from negative x, and then they run away to positive x. So those two arrows correspond to these two arrows. And then finally, in this regime over here, where we have no fixed points, we can simply put in these two arrows. So there's a very definite connection between the bifurcation diagram and the actual phase space diagram for different parameters. Okay, and we're going to make a number of these diagrams because they are very, very important in getting a feel for the solution. So once again, just to recap, you have your phase diagram, that is x dot versus x, and you have your bifurcation diagram, which is your fixed points x or x star versus r, which is your control parameter. Let's now give you another example that's slightly more complicated of a saddle node bifurcation. And the differential equation is something that looks like this. It's basically x dot is equals to r, which is your control parameter, plus x minus the ln of 1 plus x. Okay, so, and the assignment will be look for bifurcations as r varies. So the first thing we need to do is find the fixed points. And this is basically almost a recipe that you do with any partial or any ordinary differential equation. The first thing is find the fixed points x star that satisfy x dot is equals to 0, except now this thing becomes a little bit more complicated because we want to find all points x star for which this thing is true, but it's not so easy to solve because ln we don't have explicitly. So there's once again a number of tricks that you can use to deal with the situation, and I'm just going to give you one example. Okay, so that's tricky because you can't explicitly solve for x star of r, right? Because remember, you don't want it just for a specific r, you want to actually make the bifurcations and find out how the solutions change as r changes. But you can use a simpler graphical method. Rather than finding the explicit solution for r star, let's look at the graphical method. And the graphical method looks something like this. It says basically plot two plots on the same graph. The one plot is going to be y equals to r plus x. And the second plot is going to be y equals to ln of 1 plus x. Okay. So here we have it. We have y. There's our y-axis. There's our x-axis. And the first one is the line y1 equals to r plus x. So it's just a straight line. And you can see now what r does. It basically moves the y-intercept of this line. In other words, if you change r, you can just parallel transport this line up or down depending on how you've chosen r. The second graph, to plot this one, remember how you plot a ln, you first write down the asymptote. So ln of 0 goes to minus infinity. So ln of x equals to minus 1 goes to minus infinity. So there's your asymptote. And then ln is just that plot. Okay, so you should have a feeling for what a ln looks like. And now you can see how we can actually use the graphical method. So remember, as you change r, this line moves up and down, but parallel to the initial blue line. So let's see what happens if you decrease r to say r equals to 1. You've moved that blue line to over there. You can decrease r again, and you move it further down. And so as you keep varying r, you can decrease it till eventually you're going to get an r where it hits or is tangent to this ln graph over here. Okay. And that's the point where you actually solve the equation, or you create only one fixed point. If you decrease r further, you're going to go from having one solution to this equation and one fixed point as a result to having two solutions to the equation. So over here you have two solutions to the equation. You can decrease r more and you continuously have two solutions. So here you have the case of two fixed points. So if you think back of how we described the saddle node bifurcation, where you basically form two fixed points out of nothing, this is an example of how we've done so, except that we haven't actually got an explicit solution for the fixed points. We've just got the graphical representation. Okay, so let's just write that down. As r decreases, line y2 becomes tangent to line line y1 becomes tangent to the graph y2. So this is your red line over there, and there you only have one point where the two things are solved. And then it has two intersections here at the green line for even smaller r. Okay. And the statement is the saddle node bifurcation, where the nature of the solutions changes from no fixed points to 1 to 2, occurs at the tangent intersection over here when it's red. Okay, and so now we've got the graphical method. We've got an intuitive feeling for how the fixed points can be calculated. So let's actually use that to calculate them explicitly. And this is something you will use repeatedly in some of the examples. So to find the bifurcation point, you must solve both the equations that the line hits is tangent to the fixed point, and the equation that they are equal to each other at the same time. And it's actually the fact that you have two equations instead of one that makes it easier. So the condition that you have an intersection is basically this one. In other words, it's the same as your fixed point condition up here. So you want r plus x is equals to ln of 1 plus x. Okay. The condition that it is a tangent intersection is that the derivatives must also match. So you have d dx of r plus x must be equal to d dx of 1 plus ln x. And the second condition leads to the equation d dx of r plus x is just 1, and that must be equals to d dx of ln of 1 plus x, so that's 1 over 1 plus x. And to solve this equation, this is true if and only if x star is equals to 1. So this is your bifurcation point. So the fixed point at x star equals to 0 occurs when your bifurcation occurs. You then go ahead and you put x star equals to 0 back into this expression, and you get that r is equals to 0. So your bifurcation occurs at x star equals to 0, r equals to 0, which is exactly this point over here that we got from the graphical explanation. Okay, so then we say that RC is the critical value at which the saddle node bifurcation takes place, and we're done. Okay, so example slightly more complicated than the first one where we just had the parabola and we could find exact solutions, but here we can once again find the bifurcation point, and we can once again get a feel for what happens as the parameter changes. So the next step is actually to do a further analytic exploration, and this is actually very, very similar to linearization. In fact, it's linearization very close to the point at which the bifurcation takes place. So here's once again our equation. It says, and the typical question is explore the nature of the solution near the bifurcation. Okay, and remember the bifurcation takes place near x equals to 0 and r equals to the critical parameter or the critical control parameter, which is 0. And the approach is basically to keep the dominant terms in the series expansion in x and in r. Okay, so it's linearization in both in x and r. So for this example up here, what we're going to do is simply make a Taylor series expansion of this 1 plus x, and if you do that for small x, you basically get that ln of 1 plus x is equals to x minus x squared over 2 plus x to the 3 over 3 plus higher order terms. Okay, and so if we substitute this expansion into our original equation, we see that we have x dot is equals to r plus x minus the expansion. And so if we keep only the dominant terms in x and r, which is what our approach was over here, you get an equation like this. And if you recall what we did on the second slide, this is very, very similar to the equation that we got there. Okay, so near the bifurcation point, a good approximation of this equation is that it behaves like a quadratic. Okay, so recall that first example that we studied was simply x dot equals to r plus x squared, which is what I called the normal form. And it's called the normal form because almost any other saddle node bifurcation that you keep the dominant terms looks very similar to this. Okay, so the saddle node bifurcation that is in the normal form serves as a prototype for all saddle node bifurcations. Okay, and so now I'm just going to write it out more fully. Is basically the definition of a normal form for a bifurcation is obtained by making a Taylor series expansion of f of x dot equals to f of x. Sorry, to make a Taylor series expansion of x dot equals to f of x and r, where r is the control parameter, about the critical parameter rc and the critical point x star, and it captures the nature of the solution near the critical point. Okay, so that's a normal form of the bifurcation. And as I mentioned, is you can actually systematically studying all of them, because you can systematically study in one dimension the Taylor series expansions of any function in this way. Okay, so the normal form of the saddle node bifurcation always looks like this. So the saddle node bifurcation always has a normal form. X dot equals to A times R minus RC plus B times X minus X star squared. Okay, A and B are constants, and they are related to the function up here by df dr evaluated at the critical point, and df, the second derivative of f with respect to x, also evaluated at the critical point. Right. So that basically says for any function over here, if it is a saddle node bifurcation, it's going to be written in this form if you do the expansion about the critical point. Okay, and we've just verified it for our one example over here. Okay, so normal forms are very important because they allow us to classify all the different bifurcations. And so what I'm going to do now is simply continue exploring all the lowest order normal forms in one dimension. Okay, so the next one is, remember I said that fixed points can be either created or destroyed, or they can change their stability. So the next bifurcation is possibly the simplest bifurcation that allows a fixed point to change its stability, and it's called the transcritical bifurcation. Okay, and the normal form of a transcritical bifurcation that we're going to look at is simply x dot equals to rx minus x squared. Okay, once again, r is the control parameter. And let's just go, before we even do the graphical part, let's simply analyze it analytically, which is what I tend to do. Okay, we work out the fixed points and the one way of doing it is simply to factor the right-hand side, and we can immediately see that there's a fixed point when x is equals to 0, and there's a fixed point when x is equals to r. Okay, so we have x star equals to 0 or x star equals to r. The next step is you work out the stability of the fixed points. In other words, compute the derivative of this function on the right-hand side. The derivative is just r times 2 minus x star. And therefore, the stability at x star equals to 0 is just r. Okay, so the stability there is dependent on the sign of r. The fixed point at f prime at x star equals to r is minus r, so it's also dependent on the sign of r, but it is unstable whenever the one at 0 is stable, or stable whenever the one at 0 is unstable, except at r equals to 0. Okay, so stability changes as r changes sign. Okay, because we know that stability is connected to the sign of the derivative of f. Okay, and we see that this occurs when r is 0, so that's our bifurcation, where our bifurcation takes place because the nature of the solution changes there. And when r is 0, the fixed point is also 0, just by the nature of the normal form. So let's now actually draw what happens. So if r is greater than 0, you have your two fixed points at x equals to 0 and x equals to r. Always put in the actual value of r when you sketch the graph over here, the point at which your fixed point occurs, as well as the point at which the maximum of the graph occurs. Okay. So you plot the graph on the phase diagram, you put in your arrows. Where the graph is negative, it goes that way. Graph is positive, it increases. Graph is negative, it decreases. And you can once again verify that your stability, that this one for r greater than 0, the fixed point at r is stable, and this one is at the origin is unstable. And now what happens is, if r is equals to 0, this parabola sort of moves down and to the left, and you have that the maximum now occurs at x equals to 0, and you have a half-stable solution over here, in where the solution comes from infinity to 0, and this is actually a mistake. This red part should be switched to that other side. Okay, and then here, because that's the stable side, and this one is the unstable side. But anyway, this point is half stable. And finally, if r is less than 0, you can see that the parabola has sort of started up here, moved down over here, and then it moves up again. And so this thing now becomes stable, the origin now becomes stable, and the minus r, or the r fixed point, becomes unstable, remembering that r is negative over here. Okay, bifurcation diagram. We're plotting the fixed point versus the order parameter, and we can go straight to up here. So the fixed point x star is equals to 0. Okay, if r is greater than 0, it is unstable, so we give it dotted lines. And the second fixed point here at x star equals to r, okay, we know r is greater than 0, so it's going to sort of be a line over here, and we know that it is going to be stable, just as this example is. Okay, so there it is, and it's stable. Now, if r is less than 0, we know that the fixed point at the origin's derivative then becomes negative, and this fixed point therefore becomes stable. So this line is stable. And the second fixed point that occurs at at x star equals to r, which is now negative, is unstable, because that thing is positive. So this now is our bifurcation diagram. It looks very, very different from the other one. And note that this normal form is also different from the saddle node normal form, but it's very subtly different, because instead of the r being a constant, it multiplies the linear term. Okay, we're still not done with our bifurcation diagram. We've indicated the stable and the unstable points. We want to put in the bifurcation point. Oops. Over there. And label the values. We want to put in the arrows at the various parts of the diagram that reflect basically the arrows in our phase diagram. So here we have r equals to negative. So these are the arrows over here, these arrows that I've just flipped on the side and put in. Then this is those arrows that have just been put in over there. And then finally we have these r greater than 0 arrows that I've just been put in over there. So typically, to do that, you can either use these plots over here and just translate them onto this graph, or you can simply pick a point on the graph, evaluate what this x dot is, and put in the arrow in the right direction. Right. So the transcritical bifurcation is the case where you go from 2 fixed points to 1 fixed point to 2 fixed points as r increases. So it's fundamentally different from a saddle node bifurcation. And the saddle node bifurcation, just to recap, goes from 2 fixed points to 1 fixed point, and then there are no fixed points as r increases. Okay, so now the next step up, we've done every possibility we can do with quadratic terms in x. Okay, and this is basically, I said you could classify all the possible bifurcations that occur. So the necessary next step is to go and look at cubic terms. And there you actually get 2 kinds of bifurcations. Actually, you get more than 2, but the 2 we're going to study right now. And they are called pitchfork bifurcations. Okay, and what a pitchfork bifurcations, there's some very interesting physics or very interesting models that actually give you pitchfork bifurcations. What happens with them is you have fixed points that appear in symmetric pairs. Okay, so the physical problems where this fixed points occur is typically physical problems where you have symmetry. So you have the case where, remember I said you could have this vertical beam, you put a weight on the top, initially nothing happens, but make it heavy enough, or like a ruler or something, make the weight heavy enough, and eventually the ruler is going to bend, but it's going to bend either left or right, and it doesn't really matter, it's just going to choose a side. So in some sense you have a symmetry in the solution, and that's usually where you get Pitchfork bifurcations necessarily has to have that symmetry. Okay, and now what's interesting, you have two types. They look very, very similar, but they are vastly different in what the properties of the equation is. So the first one is a supercritical Pitchfork bifurcation, and the second type is a subcritical Pitchfork bifurcation. A subcritical one is very explosive and very dangerous. If you get a set of differential equations where a subcritical bifurcation takes place, you must be very wary of what can happen in that scenario. In fact, typically you get these type of equations appear when you model really explosive situations. Okay, so the normal form of the two things look very, very similar. So the supercritical Pitchfork bifurcation is just Rx minus x to the cubic. The subcritical one is Rx, and there's this plus sign over here, plus x cubic. Okay, as I said, vastly different phenomena are described by these situations. So let's first look at the tame one, the supercritical one. So we have x dot squared equals to x times r minus x squared. We factored it. We now have fixed points, and remember I said you must say when these fixed points exist. So the first fixed point is here at x equals to 0 and exists for all r. The second set of fixed points is x star equals to plus minus the square root of r, and this is only true if r is greater than 0. Okay, next step, we work out stability, which means you have to basically differentiate this thing to get f prime. So f prime of x star is basically r minus 3x squared. And so at the origin, the stability is simply r. So you see here the stability depends on whether r is positive or negative. Okay, the stability of the other two fixed points is in other words, x star equals to plus minus square root of r is equals to minus 2r. Okay, so these fixed points have different stabilities, and the stability also varies as a function of r. Okay, and in fact, this fixed point, remember, it only exists if r is greater than 0, so it is always stable. Okay, the bifurcation occurs at RC equals to 0 and XC star equals to 0. That's our bifurcation point. It's where the nature of the solution changes. So at this bifurcation point, we basically go from having one stable fixed point to having 3 fixed points, of which you have 2 stable ones and 1 unstable one as R increases. So let's just draw the actual phase space diagram. So if R is greater than 0, then we have the 3 fixed points. And the 3 fixed points are basically 2 stable ones over here and 1 unstable one. And the analysis is exactly the same as what we've been doing. We basically take this f of r, we draw the graph. Okay, to draw any graph, you need to draw the x-intercepts. You draw the maximum values, and you actually put the value in here. In other words, where the derivative of f is equals to 0, what the function is evaluated there. Okay, so you can actually put in that x value as well, if you want. You put in the arrows, the flow arrows, so the graph is negative, decreases, increases if it's a positive over there and decreases there. Indicate your stable and unstable fixed points, and there you have what the phase diagram looks like for r greater than 0. If r equals to 0, the differential equation you're studying is x dot equals to minus x to the 3. Okay, and you can actually solve this thing algebraically because you have dx over minus dx to the 3 equals to dt. So t is just equals to some constant times x to the minus 2 plus c. So that's why I said x approaches 0 algebraically over here. And finally, if you have r less than 0, you have this cubic that's much steeper, and so you can see that r, and so near the fixed point over here, the graph basically behaves like the linearized version is x dot equals to rx. So it basically approaches 0 exponentially, and it is globally stable. In other words, all solutions come to the x equals to 0 point. The bifurcation diagram, let's draw that, how the solution changes as a function of r. This is the fixed point x. We first draw in the 0 fixed point, okay, so the fixed point at x equals to 0 is stable when r is negative. It is unstable when r is positive, because remember it depends on r, and therefore the sign determines the stability. And the fixed points at x star equals plus minus the square root of r. Okay, so if x for the plus square root of r branch over here, we have that it is stable for r greater than 0, because this thing is negative. And the lower one has the same derivative value on the fixed point, and it is also stable. So you can see now where the thing gets its name from. It basically looks like a pitchfork or a hayfork, and you sort of have a stable branch that then splits into two stable branches with an unstable branch in the middle. And this point where it occurs is the bifurcation point. For this model, it's just 0, 0. We once again, to draw the diagram completely, you put in your arrows that indicate the flow. Okay, and here it's just at this point, if r is positive and x is negative, it is always going to flow towards the stable branch. In other words, that fixed point. If r is positive and x is positive, it's always going to flow to this stable branch over here, this fixed point. Note that the arrows always flow towards stable branches and away from unstable branches. On this axis, the r equals to 0 axis, it's just this situation. They both flow towards a stable fixed point, and over here they are on the stable fixed point. So, for example, this region over here would represent the case where your beam isn't buckling, and then when you get your maximum weight that the beam can take, you get your bifurcation point, and then when you increase the weight that you're putting on top of the beam, it's going to buckle, and it's either going to buckle left or it's going to buckle right. But both of those situations are stable, at least until the beam breaks. Okay. The cubic term, so one comment over here, the cubic term in a supercritical pitchfork bifurcation is stabilizing, in the sense that it's stabilizing in the sense that it stops the solution exploding. So whenever x gets large enough, x dot becomes negative, okay? So you're out here, and that pushes it back to the fixed point. So if x is negative enough, it's going to increase and it's going to actually hit the fixed point. So this negative term over here is stabilizing. And now you can see what's going to happen in this other case where it's positive. It's not stabilizing. The solutions run away. So let's do that. That's the last slide. So the pitchfork bifurcation, once again, the cubic terms, you have the two cases, and I'm now going to look at the subcritical case, which is this thing. Okay, so here the cubic term is destabilizing. When this is the normal form, you typically get violent explosions. So an example is the Fukushima reactor, as well as Chernobyl, are examples of really violent pitchfork bifurcations that went terribly wrong. Okay, and I'll try and show you why it happens now. So let's analyze it again. Same analysis the last time. Fixed points exist, so x star equals to 0 exists for all r. X star equals to plus minus the square root of r only exists for r being negative. Stability, work out the derivative of this guy, and there it is. And now we see that at the origin, the derivative is equals to r, so it changes with the value of r, the stability. and the stability at the two branches is equal to minus R. So once again, the fixed points when R is negative have different stabilities. And once again, you have the situation where you go from 3 fixed points to 1. So that's not changed, but the way the stability changes has in fact changed. Okay, the bifurcation takes place at RC equals to 0 and X star is equals to 0. You have the case where you have 3 fixed points, 2 unstable and 1 stable, right? The fixed point at the origin is stable because R is negative. The 2 fixed points of the 2 branches are unstable because R is negative there. And that then goes to 1 unstable fixed point as R increases. So we can do the same graphical analysis as we did for the supercritical bifurcation. If R is greater than 0, you have only 1 fixed point because this other one does not exist. But now, because the cubic term is the term in front of the cubic is positive, it looks like a cubic, and therefore the velocity increases over here, so it runs away to infinity in that direction very quickly, and to negative infinity to this direction is very quick as well. So if R is greater than 0, you have no stable fixed points. If R is equals to 0, you have the same situation. We have x dot equals to x cubic. So it once again diverges to infinity, but algebraically, you can once again solve this equation analytically. And over here, where R is less than 0, you have a stable fixed point surrounded by 2 unstable fixed points. Here, so anything greater than x equals to the square root of minus R is going to run to infinity. Everything less than x equals to minus the square root of minus R is going to run to infinity. And so you're only going to have a very, very small region that actually approaches the origin. And so let's just draw the bifurcation diagram. Once again, we have a stable fixed point at the origin if R is less than 0 coming from there. And we have a unstable fixed point if R is greater than 0 at the origin. But if R is greater than 0, we also have, if R is less than 0, we also have these 2 other branching fixed points. In other words, plus minus the square root of minus R. But we show over here that both of them are unstable. So there they are. Okay, so there are the 2 unstable fixed points. What we're also going to do now, our bifurcation point again occurs at x star equals to 0, R, C equals to 0. And we put in our arrows. And here you can see the fundamental difference. Whereas in the supercritical case, the whole solution always approached a fixed point. Here, only this solution in the small region approaches a fixed point. Okay, anything be above this pitchfork runs away to infinity, and this thing also runs away to infinity. And then when you get to the bifurcation point, suddenly the stable branch completely disappears and everything just runs away to infinity. So that's why I said, and it runs away very quickly. That's why I said it usually, if you have this type of normal form occurring, you're modeling a violent explosion, and you must be very, very cautious to ever you advising where this equation arose. Okay, so here we have the strange situation where the stable solution ends at R equals to 0. And the cubic term basically drives the solution to infinity in a finite amount of time. So the example of a stable solution that went bang is the Beirut explosion that took place, I think, a year and a bit ago now. So basically there was a stable solution where the nitrogen also was stored in that silo. If the temperature didn't get too hot, it would be fine. But if something just drove it out of the stable solution, it just completely exploded. And it's a very pitchfork, nasty bifurcation that took place. Okay, so that concludes my sort of classification of the possible bifurcations or the low order bifurcations in 1D systems. please go through this thing carefully. It's a very important part of our understanding of dynamical systems, and a lot builds on this thing. And my experience is that usually students find it quite challenging, so it will be well worth your while to go through this lecture again, as well as to try some of the problems and look at Strogatz's textbook. Thank you very much. That's enough for me for now. Until the next lecture.